Hi, everybody. Welcome back to Dave's Math channel. This is my continuing feature on the Math Lovers book. And as I do every Saturday, I'm featuring another biography of a famous mathematician. And this is a big one, Joseph Fourier. He lived from 1768 to 1830. He was a French mathematician. I'd say he's probably in the top 20 of all the greatest mathematicians of all time. But anyway, let's get started. So here's a picture from my book about Joseph Fourier and my description of him. But it's probably better just to show you some diagrams. His main claim to fame was Fourier's series and Fourier transforms, and I have a whole video on that one, which I highly recommend you guys watch. I'm just going to give a very brief overview of them. Uh, but anyway, Fourier's series. The way you're supposed to think about Fourier's series is the way you build up waves. It turns out that every wave, every periodic function, in other words, which represents the sound from any musical instrument. When you play a violin, if you play a violin string, or if you pluck a guitar string, or if you play a key of a piano, all those instruments, when you play a note, gives you a waveform. But the waveforms can be pretty complicated. The shape depends on the instrument. But what Fourier discovered was that every waveform, no matter how complicated it is, as long as it's periodic, you can write it as a sum, or I think in math and physics people like to say superposition, but it's really just a sum of sine waves, and a sine wave is just a function, a sine function, which I'm sure you guys learned in trigonometry. These nice smooth waves that just go up and down, and a smooth wave showing the different colors in the background. So this picture, this is a really nice picture, I think. What this picture is showing is how you would build up a square wave. And a square wave is a wave where, the oscillations are square, like they jump up to a fixed value, then they jump down to a fixed value. Well, it turns out even that one, that doesn't look anything like a sine wave, but it turns out you can build it up from sine waves. And if you use just six of them, you get something that looks pretty close to a square wave. And you can do that with any wave. And here's another picture of square waves. This just shows the first four terms in the Fourier series. So you don't even need that many terms to get a pretty good approximation of the function you're trying to approximate. Um, and so that's Fourier series. There's another important thing, which is kind of a generalization of Fourier series. It's called a Fourier transform. And the nice thing about Fourier transforms, it's the same idea. You're breaking up a waveform, but it doesn't have to be periodic in the case of a Fourier transform. In the case of a Fourier series, it's always a periodic function. And that gives you a Fourier transform, a discrete, with a bunch of delta functions, a bunch of spikes. And each spike corresponds to a particular frequency, a particular sine function with a particular frequency, but it doesn't have to be periodic. I mean, these other three, the one on top this is a pure sine wave. Then a pure sine wave, the Fourier transform is what's called a delta function. It just means that there's only one frequency in that sine wave, which is like an infinitely tall peak and infinitely thin. That's called a delta function. But then you could start with this, the second picture on the left is more of a kind of a generic, what they call a wave packet, or a wave function. You see these a lot in quantum mechanics. And it turns out the one shown here, the Fourier transform, is this kind of block function. And what that means is that you have infinitely many frequencies it's made up of, but they're all within a given range. And then I think the most interesting of these to me is the third one. If you start with a Gaussian wave packet, that has the same shape as a bell curve or a normal distribution, which is widely studied in statistics. It also turns out that you get waveforms sometimes that look like Gaussian waves. And if you start with a Gaussian wave and you take a Fourier transform, that gives you back a Gaussian. So in other words, it's something that has a Gaussian shape in the time domain. If you take a Fourier transform goes from time domain to frequency domain. So if it's Gaussian in the time domain, it's also Gaussian in the frequency domain. I just thought I'd mention that. And there's a fourth example in the bottom, double exponential. This is another pretty common example. It's a little like a Gaussian, but it's more peaked at the, has a cusp on top. And then its Fourier transform looks sort of like a Gaussian. It's called a Lorentzian. So those are just some common examples of Fourier transforms. This is very, very important in like signal analysis. One thing that I think if Joseph Fourier, he lived in the 18th and early 19th century, and I think during his lifetime there weren't a whole lot of applications of this theory. And actually, you'd think that, I would have thought that the thing he would be most interested in was music, because, like I was talking about musical instruments, how every note has a particular waveform. Maybe he did consider that at some point in his life, but that was not his initial problem he was interested. He was interested in heat conduction. And you can apply Fourier series to calculating heat conduction along a rod, it turns out. There's something called the dispersion equation, and you can use Fourier series in analyzing the solutions to heat transfer equations. I think that was the main thing he was interested in as far as Fourier series goes. But the thing that I wonder what Fourier would think if he could see us today. I mean, there's so many applications of Fourier series. They're just all over the place. You can't get away from them. Like digital cameras, they use Fourier analysis in the way they take pictures. When we do like JPEG images, you do Fourier analysis. They're all over the place. And I think I'm just going to talk about one more application. There's something called the fast Fourier transform. It turns out there's another type of Fourier transform I didn't talk about. It's called the discrete Fourier transform. You don't have to take the Fourier transform of a continuous function like a wave. You can take a Fourier transform of a discrete function. That's just a function that's defined over the integers or over some discrete set. It turns out there is an analog of the Fourier transform for discrete functions. And I think one of the most amazing applications of discrete Fourier transforms is a thing called the fast Fourier transform. And this allows for some very, very fast computations that would take much longer without using it. A good example is multiplication. It turns out you can multiply two really large numbers using a fast Fourier transform, and the running time is order of n log n, which is much much faster than shift and add. Shift and add is probably what you learned in grade school, and that's the order of n squared, O of n squared. Well, fast Fourier transform is O of n log n, which isn't that much slower than O of n. So pretty amazing that you can multiply numbers so fast, and we can do it using a fast Fourier transform. Just thought I'd mention that. And this schematic kind of shows you how it works. I'm not an expert on this, but I think another application of fast Fourier transform is neural networks. This looks like a neural net, the way this thing works. And then I think I'm just going to say one more thing that Fourier is known for. He actually discovered the greenhouse effect. I think in 1792, and I think you guys are all familiar with the greenhouse effect. It's how greenhouses work, and it's also responsible for climate change, which used to be called global warming. Now they just call it climate change because they don't know whether it will result in a global warming or a global cooling. It could trigger an ice age. It could if enough ice from the poles, once it starts melting, gets into the Gulf Stream, that could trigger another ice age. We don't know what the effect's going to be, but it is unanimous. I just want to say one more thing. I hope I don't get in trouble with any of this. Is actually scientific fact. Climate change is real and it's caused by man. Every serious scientist in the world knows this. And the only so-called scientists who have been debating this are ones who've been hired by the government they're like spin doctors. They've told people what they want to hear. This was true during George W. Bush's presidency. He denied climate change as being real or being caused by man, and Trump is doing the same thing. But this is real. It's going to affect us. I don't know how seriously it's going to affect us. How seriously it affects us depends on what we do right now. I think all we can do at this point is minimize the catastrophic effect that'll result from the greenhouse effect. And just to clarify, in case you guys don't know what the greenhouse effect is, it's caused by what are called greenhouse gases in the atmosphere. I think the biggest one is carbon dioxide, CO2. And I'll just give you a little overview. The CO2 content of the atmosphere has been increasing. There is good, solid scientific evidence that this has been happening since the 1950s at least, but even probably way before then. I think it started increasing during the Industrial Revolution in the 19th century because what happened was burning fossil fuels, burning coal and oil and natural gas. What happens is they leave carbon dioxide in the atmosphere as a byproduct of their burning, and carbon dioxide blocks sunlight. So what happens is, you get light from the sun coming in on the Earth. Without so much carbon dioxide, you have sort of a balance where the same amount of radiation goes out as goes in. But if you have too much carbon dioxide, the CO2 will trap the sunlight in the atmosphere because it can't get out. It's opaque to UV radiation from the sun. So the UV radiation from the sun gets trapped in the Earth's atmosphere, and it causes the atmosphere to warm up. This is known, and this has been studied since the 1950s. And as a matter of fact, Joseph Fourier understood the mechanism behind it. He was the first person to understand the mechanism behind the greenhouse effect. And maybe he'd be really delighted to see all the applications of Fourier series and Fourier transforms today. I think he would be appalled by the fact that we're letting climate change potentially destroy the planet. So I don't know if he'd be happy or sad if he were here today, right now. Maybe a little bit of a combination of both, kind of like I am. But anyway, that completes my video for today. My profile on Joseph Fourier. Like I said, I think one of the greatest mathematicians of all time. Anyway, thank you for watching. Long live math, and I'll see you guys next time. Bye.